Hello everyone, my name is Suvaporn Homjandee. I'm a master student from Chulalongkorn University from Bangkok, Thailand. Today I'm pleased to be here to present to you my research on topic a random foliate with minority condensations and decision trees for class imbalance problems. Outline of these presentations, I will begin with an introduction to give a little bit of classifications and mentions about class imbalance problem, and then I will move to the background knowledge that are minority condensation, decision trees, or we will call it MCDT, and talk about a little bit of random foliate algorithm. After that, I will expand to our research methodologies, conduction the random foliage of mixed decision trees, or we will call it RMDT, and then experiment and result. And finally, the end of this presentation is a conclusion. Let me start with an introduction. What is classification? First, I would like to expand that classification is a part of machine learning, and machine learning is one of the study of artificial intelligence. Machine learning is teach computer to learn, and the process of teaching computer to learn depend on the data on past experiments from real-life situations. Second, machine learning model, and third is optimization parameters. And one of the most important aspects of machine learning is classification. The goal of classification is to develop a classifier that can anticipate the target or class of intents based on our historical dataset. And conducting classifications applied in our real life, being used in the variety of fields such as medical detections based on information from the health care of patients, or to approve the loans, identify default or non-default loans, and marketing field, the classifications of a product or service to meet customer to be able to organize promotions or continue marketing plans. And however, classifications algorithms have difficulty generate and approximate classifier when faced with the real-world dataset having a small number of intents for some classes. So, an imbalanced classification problem is one in which the distribution of example across recognized classes is uneven or biased. The distributions can range from a little skewed to a severe imbalance, with one example in the minority class for hundreds, thousands, or millions in the majority class. Because most machine learning algorithms for classifications were created with the assumptions of an equal number of samples for each class, imbalanced classification provides a difficulty for predictive modeling. As a result, models with weak prediction accuracy, particularly for the minority class, emerged. This is a concern because the minority class is usually the most important, and so the problem is more sensitive to classification errors for the minority class than the majority class. For example of imbalanced dataset, the left-hand side figure is an imbalanced two-dimension data. You can see that the number of red dots are less than the number of blue dots. It is clear that the proportions of class is no balanced. And figure at right-hand side on the right-hand side show the importance of the class. With a small number of a class that had a larger number, you can see that even if the number is late, it doesn't mean it's late important. For example, in a credit card fraud detections, there is a small number of fraudulent transactions, but they unusual and must be discovered. In the same way as disease diagnosis, the perception of disease patterns is more significant than normal people. In the binary classifications, the majority class is normally represented by the negative, while the minority class is represented by the positive. In the real world problem, the minority class is frequently more important and receive much attention to correctly classify. And recently, many methods had been presented to deal with the class imbalance problem, where it can be categorized into 4 different approaches. They are first a data level approach, second algorithm level approach, and third is a cost sensitive approach, and the last one is an ensemble approach. In our research interest is the study of algorithm level approach, since it does not cause any shift in the data distribution and is more adaptable to various characteristics of imbalance dataset. And next, in 2019, 2 years ago, the minority condensation entropy, or MCE, is a splitting measure that is proposed that can build a addition tree to classify minority intents, and the addition tree that is built based on this MCE is called the minority condensation decision trees, or MCDT. Before I'm going to talk about MCDT, I have to talk about a little bit of the splitting measure called minority entropy, or ME. Because of minority condensation entropy, or MCE, is a entropy that is modified from minority entropy. It fixes the problem of Shannon entropy that bias toward the majority class by keeping the majority intents within the minority lengths, and then it used intents within minority lengths build decision trees. In the path of the computations of MCE is based on the interquartile length rule, or IQR. This is the import to the set of minority intents values for detecting the outlier. For detecting the outlier, it defines the boundary that represent the ranks of acceptable values for the minority intents based on the Turkey block plot. The lower inner fringe is defined by the first quartile minus 1.5 times of IQR, and the upper inner fringe the upper inner fringe is defined by the third quartile plus 1.5 times of IQR. For example, this figure demonstrates the use of the IQR rule. The set of intents within that rank is considered which the minority class is more condensed, and then intents within the ranks are computed by Shannon entropy. So entropy computing with intent in first and third quartile is called MCE. The decision trees is built based on MCE is called correct minority condensation decision trees, or our MCDT. Also, the idea of developing an algorithm to build the random forest classifier that is suitable for classifying and imbalanced datasets is one of the methods that have received wide attention. The random forest algorithm is a collection of small decision trees with sampling feature to classify intents and selecting the class that was predicted the most from each tree to be the final prediction. And then this slide show the framework of random forest algorithm. We can see that it had two important steps that are first, bootstrap on a training set, and second is building decision tree from the different subsample and randomized attribute. A bootstrapping on an imbalanced dataset at figure 7 and figure 8. It is a dataset before bootstrap and after bootstrap respectively. We can see that it make the number of minority intents less than before, and it has a chance to make minority intents disappear, and the predictions performance of the classifier are decreasing. So from this problem, we are interested to bring improvement of algorithm coping with the imbalance problem. And next, we will move to expand about our methodology. The motivations of our research come from the success of using the decision tree classified based on MCE to handle the class imbalance. It fixed the problem of the ME that sometimes it unnecessarily widens the minority length, which cover more majority intents because of having minority intents values extremely deviate from order within the dataset. These reasons make MCDT highly successful in handling the class imbalance problem, and however, the standard decision tree still outperform for predictions balanced dataset. So in this research propose an algorithm that is random forage of mixed decision trees and MCDT, and contractions of RMDT consists of two parts. First, bootstrapping step, we will maintain all minority intents and bootstrap that majority intents. However, in this section, we bootstrap until the number of majority intents and minority intents is equal. So data set is balanced subsample, is already balanced subsample. The decision tree will be built using the standard entropy, that is Shannon entropy or SE. And then the second part, we will also bootstrap only majority intents and keep all minority intents in a training data set, but this part we will ignore the balance of these two classes. So subsample from this part are imbalanced, and MCE should be used to discover the best attribute to split in each decision trees. And from these two parts, then we have our model IMDT model, which user can control the number of trees in the forest. In this research, we let the number of standard decision trees and MCDT is equal. Finally, compute the performance of MCDT and compare it with other algorithm. And after that, I would like to bring you to the path of experiment and results. The efficiencies of classifier in the class imbalance problem is evaluated quantitatively based on the predictions and recalled with and derived from the confusion metric at the figure 9 at right hand side. Recalls exhibit how many relevant items are selected, that is the number of two positive divided by the number of two positive at field negative, and precisions exhibit how many selected items are relevant. It computes from true positive divided by the number of true positive and field negative. Another measure are F measure and geometric means. Both of them are the performance measures that are suitable for a class imbalance problem with harmonized recall and precisions. Parameter beta in F measure is the weight of importance between recalls and precisions is what you set to 1, which means they are equally important. This graph shows the difference of precisions, recalled F measure and geometric means. F measure and geometric mean, for sure both of them show the difference of the values between precisions and recall, but the F measure being more deep negative than the geometric means, and the values of them are between 0 and 1. If we let X axis is a classifier that make the different performance values, and Y axis is the performance values from 0 to 1. Blue line is the precisions, orange line is a recall, gray line is a F measure, and yellow line is geometric means. If precisions and recall are more different in the late cycles, if precisions and recall are more different, then F measure and geometric means return low values follow the precisions and recall. And in the other hand, if recall equal to precisions, then F measure and geometric means return high values. Okay, the experiments were performed on 20 imbalanced binary datasets. 10 of these datasets are from synthetic datasets consisting of 10 groups of experiments having different percentages of minority intents from 5% to 50%, and then we repeat for 20 times for each experiment. In each group consists of 500 intents and 50 attributes. Each class is formed as a Gaussian cluster which is located around a centroid in 2 dimensions. For each cluster, informative attributes are drawn independently from normal distribution that have mean equal to 1 and variance is equal to 0. The clusters are then paired on the centroid. The average results of F measure and geometric means are shown in this slide. They present the values of both RMDTs and standard random forest or RF increase when the percentage of minority intent increase. Evidently, RMDT outperform random forest when the number of minority intent is tiny, whereas their values will approach to 1 when a dataset is more balanced. This confirms that standard random forest may not be suitable to deal with the class imbalance problem. And then for classifications, we select another 10 datasets from real-world applications and sorted the imbalance ratio from smallest to greatest. The comparisons of the average performance corresponding to its evaluation metric is shown in this graph. The higher value indicate the better performance. Green, the light green is our algorithm RMDT, and yellow is standard random forest RF, and blue is MCDT, and pink is another classifier that is at the boot. The high values indicate that the better performance. Comparing the precisions of our classifier, RMDT yields the highest average performance, which are better than other methods. It offers the best results over the other. Moreover, for comparisons by recall, IMDT used the similar average performance to random forest, standard random forest and attribute which is better than MCDT. For comparison by F measure and geometric means, they exhibit the same result. IMDT used the highest average performance better than other classifier. It also offers the best result over the other on average. Okay, and we are going to the end part of this presentation. That is conclusion. This research presents a random forest of mixed decision trees and the classifier that successfully handle the class imbalance problem. Minority condensation decision trees with arise from extending the minority entropy concept. From comparing performance by two collections of experiments with a synthetic dataset and real-world datasets from UCI. In the performance comparisons using F measure and geometric means, our classifier outperform other classifiers and also outperform the standard random forest, MCDT and attribute on all metric, recall and precision. RMDT or our method is successful is dealing with the problem of class imbalance, but it doesn't function with a dataset including categorical quality of multiple classes. So our proposed algorithm need to be generalized to be able to apply to a multiple class imbalance dataset with any type of attribute, such as dealing with multi-class datasets consisting of both categorical attribute and numeric attribute. And okay, we have to say thank you my faculty Applied Mathematics and Computational Science AMCS program, and thank you my scholarship Science Achievement Scholarship of Thailand DPST for supporting me. And this is all reference. Okay, thank you for your attention.